In this video we review the most common types of decays that happen in nuclear chemistry. Well, as we've said in the introduction to this series of videos on nuclear chemistry, of the 2,000 or so nuclei that we know, only about 279 or so are stable. The rest tend to undergo decays. So again, what we're going to do here is try to review the most common types of nuclear decays. There are two main classes of nuclear decays: those in which the mass number changes and the ones in which the mass number doesn't change. Okay, so let's start with the ones where the mass number changes. That's actually only one of them that we're going to study, and that is alpha emission or alpha decay. Okay, so there is going to be alpha decay. And an alpha particle is simply a nucleus of helium-4. Okay, that is what is an alpha particle. All right, so let's see if we can then try to write an example here for how these nuclear decays take place. All right, so we're going to look at the decomposition or the decay of uranium-238. And then uranium has an atomic number of 92. And uranium can undergo alpha decay into thorium. Okay, and then that emits an alpha particle. All right, so the thorium atom has 90 protons, and that particular isotope needs to have 234 neutrons. All right, so something that is important about these nuclear chemistry equations is that the sum of protons and neutrons in reagents and products has to be the same. Right, so notice that if we add up all of the protons that you have in products, that is 92, that is the same thing as the number of protons that you have in reagents. And then the same thing happens for the mass number, and therefore for the number of neutrons. Okay, so we're always going to be keeping track of whether our nuclear decays are correct by just making sure that, again, your atomic number and mass number are conserved as you go from reagents to products. Clearly, alpha decay is a process where the mass number changes, right? Notice that you're losing mass in the nucleus, okay? And again, that's because you're emitting a particle that has a mass, that is the helium atom. All right, so the rest of the decays that we're going to consider in this video are going to be those in which the mass number is conserved. Okay, so the first of those types is going to be beta decay, where a beta particle is an electron. Okay, so the electron, remember that is doesn't have a mass number, okay, and has an atomic number of -1. All right, so then let's try to write here an example of a beta decay. Okay, so that thorium atom that is generated in that alpha decay of uranium, okay, which is 234-90. Okay, that can decay to protactinium, okay, and notice that the mass number doesn't change, okay, but the atomic number goes up by 1. Okay, electron 0 -1. All right, so let's make sure that our equation is correct. Okay, notice that you have here 90 protons and then 90, and then the mass number doesn't change, which makes sense. Okay, so effectively, what has happened in this transformation is that you have increased by 1 the number of protons, but the number of neutrons, the mass number hasn't changed. Right? So what that means is that effectively, what this means is that you have changed a neutron into a proton. Right? Notice that in this transformation, you don't change the mass number, but the atomic number changes. All right, and that is exactly what we have here. So effectively, what happens is that there's a transformation of a neutron into a proton, and that also is accompanied by the emission of a beta particle, which is a high energy electron. Okay, so there is the beta decay. So let's study a couple more of these decays. The next one is called positron emission, and this requires us to define a new particle. So we have the proton, we have the neutron, we have the electron, those three. Okay, so there's a fourth player that we're going to be talking about, and that is the positron. Okay, notice that the positron would be the antiparticle of the electron. Okay, all right. So let's see a couple of examples, or one example in which we have a process with positive emission. So think about the sodium 2211 nucleus isotope to go to neon 2210. Okay, and again, this carries the emission of a positron. As always, we double check that our nuclear equation is correct. We have 11 protons in reagents and in products, and then the mass number is also 22 in reagents and products, so that seems to be correct. Okay. Now, this effectively, what we can actually see is that, well, you're reducing the number of protons, but the sum of protons and neutrons is the same, so that must mean that a way to understand this would be the change of a proton into a neutron. Okay, that is effectively what happens, and that is accompanied by the emission of a positron. Now, this positron is interesting because, again, we have said that it's the antiparticle of an electron. So we can now take this and discuss what happens when you have a particle interacting with an antiparticle. And in this particular case, what we actually know is that when you have an electron colliding with a positron, their antiparticles, you actually emit very high energy electromagnetic radiation. Okay, that is gamma rays. Now, this is extremely interesting because this shows you the transformation of massed particles. Okay, so even though we actually have particles that do not contribute to the mass number, they still have some mass. It's just that the mass is much smaller than that of a proton or a neutron, right? The mass of an electron is about 1,800 times smaller than the mass of a proton. Okay, so these are mass particles, but then when they annihilate, right, when they combine, you actually generate energy, electromagnetic radiation, which is not, doesn't have any mass at all. Okay, so that tells you that there's clearly a relationship between energy and mass, okay, which is what the theory of relativity actually tells you. Again, but that's an example of the type of processes that we worry about in nuclear chemistry. Okay, all right. So the last nuclear decay that we're going to be talking about is called electron capture. Okay, so we can hear, and this is going to be electron capture. And an example that we can put here is going to be mercury, okay, which has 201 mass number and then 80 protons, and that can turn into gold, which has 79 protons and 201 mass number. Okay, let me actually erase that. You capture an electron, which is like this, and then you generate gold, which is going to have 79 and then 201. And then this usually is accompanied by the emission of high energy radiation. All right, so let's make sure that this nuclear equation is well balanced. We have 79 protons in reagents, and then 79 in products. That is good. And then here we have 201 and 201. That is correct as well. Okay, so what happens is that this mercury atom captures an electron and then turns into a gold atom. That would be perfect for alchemists, right? People who many hundreds of years ago were trying to generate gold out of other metals. Okay, the problem is that these processes have very, very, very low rate. Okay, so they're impractical for the synthesis of gold. Okay, now something that is important is that this electron actually does not come from the outside of the atom, right? So we're not bombarding this mercury with electrons to try to turn it to gold. Now, this actually is one of the electrons of the mercury atom, right? So if you write here mercury, if the mercury atom is neutral, you actually have 80 electrons, right? Which are distributed in the atomic orbitals that we have studied elsewhere. So it turns out that this electron usually is from an inner orbital, so maybe a 1s orbital, 2s, those types that actually gets absorbed by the nucleus, and that's where the nuclear process takes place. Okay, so again, this is an inner, what we call an inner orbital electron. All right, and again, this usually is accompanied by the emission of high frequency, high energy radiation. All right, so this is going to be the 4 types of decays that are more common, the ones that we're going to be studying here in nuclear chemistry. And again, we can distribute or separate this in between this process in which the mass number changes, and then these other 3 processes in which the mass number doesn't change.